Hey, Peyton.
Hi, Brian. How are you?
I'm doing fine. How are you?
I'm doing well. I totally
Yeah,
forgot.
I was good. I got, it's okay. I saw your 42 out of 45. That's all good. Um, did you want to go over your mistakes or did you already go over your mistakes for that midterm?
I completely messed up the synthesis. I think
Uh-huh.
that's where I got most of the points off.
Yeah, can I see it? You can send it to me on the school website and then I could like look through it and then we could like look through it together.
Oh, yeah, of course.
Mhm.
You said to send in the chat or it's the
Yeah.
school thing.
Yeah, either way works. The Zoom chat or the school thing would work.
Okay, okay. Website, let me download that.
Mm-hmm. Did you do much better for this one than the first midterm, or how did you do for the first one? I forgot to ask you for the first midterm.
Which is good, I guess. It's not terrible, but I wish you do better on the third one.
Yeah, I see. It's good. Hmm. So your
Okay,
first
sorry.
one will be your drop one for sure. Hopefully.
Yes.
Yes.
Are you walking right now to a place with better Wi-Fi?
Okay, okay. Are you at the library right now?
No, I'm at the Green in West
Mm.
Village, and
Hmm.
the West Village Wi-Fi is troubling.
Oh, sure. Yeah, I've been there before for some tutoring sessions in person there before. There's like the student lounges are very nice actually, like with the big whiteboards.
Oh yeah, those are nice.
Mm-hmm. Yes. And we're gonna do our two hoodie sessions soon, like for midterm three and the final.
Yeah, I hope to do one for midterm three and one for the final because I've heard the final was really, really tough.
Oh yeah, it is like the last week or last 2 weeks is like 20 reactions, like a lot of reactions thrown at you. So get ready to get ready for that.
Oh no. So the strat would be to like prepare for it
Yeah,
way
get ready
beforehand.
for it ahead of time because the upcoming midterm, the hardest reaction would be Deal's Honor for sure, with all the
Hmm.
regional selectivity, stereo selectivity, and the rule. The benzene reactions are not that bad. Like they're like actually pretty uh doable, the benzene reactions. But after the midterm three material, once we get into ketones, aldehydes, and enolates, like enolate chemistry, that's when it hits hard, like with all the acid-base reactions, for reverse mechanisms. Um,
Aw.
so don't get overwhelmed because there will be a lot of reactions thrown at you, but they can be categorized into like four or five different categories of reactions that is like the same mechanism, just different reagents,
Mm.
different direction, but it's like it can be categorized and organized in a clear way. And I can show you that in office hours and our sessions as well.
Okay, awesome.
Uh-huh. Yeah.
So do you suggest that we start studying like 1 or 2 weeks before the midterm?
Uh-huh.
I mean the
Do
final.
for the final, so I would first focus on midterm three, and right after midterm three, because your midterm three is week 9, start studying for the final right away because like your other classes will get in the way, and then you're gonna see like
Oh yes,
as
yes.
a week 10 goes by, it's gonna be so crazy. So after midterm 3 on week 9, that's when you should get ahead. But right
Oh
now,
yes, yes,
focus
yes.
all
I'm
your energy
definitely
and
gonna
time
do that.
on studying for midterm 3.
Okay, yeah.
Yeah. Mhm. Yeah.
Wait, I'm gonna ask my friend Crystal to join the Zoom and send you the the exam because
Okay.
my Wi-Fi is really bad.
Yeah, of course, of course. I heard you guys
One
go
sec.
to the library and watch my office hour videos sometimes at the big TV, big screen. Hey, Crystal.
Hello.
How did your midterm go? Your midterm too?
It was,
Like,
it was better than the first
that's
one, but
good.
I still hope to do better,
Better.
improve every time.
Yeah, of course. But improvement though, right? From the first midterm? That's
Yeah.
good, yeah. We'll aim better for midterm three for sure, which I think should be doable because midterm three with the benzene one is good, but the Diels auto reaction is what you have to be careful of.
Okay.
Yeah.
Just send it here.
Yeah.
I don't know how.
Mhm. Let's see, chat. Are you on the iPad, laptop, or phone?
Talk.
Oh, laptop. Okay. If you click
Email
on
it to you.
chat, yeah, you can email it to me, or you can send it to the Zoom chat file or school. Either way, whichever way is easier.
Can you please send me your email?
Yeah.
Yes.
But I heard the average for this second midterm was also higher than the first midterm, which was unexpected. I thought the second midterm would be lower average.
Yeah, it was unexpected, but
Yeah.
I think it was everyone improved.
Yeah, definitely. They knew how to study better. They did more practice probably.
Yeah.
That's good.
It's just taking a while.
No, it's okay. It's okay.
Okay, there we go.
Mhm.
Okay, I sent it.
Okay. Let me see. So I'm gonna take. Oh, I see it. Okay. Um. Okay. Do you guys have the same section? Section A.
Yes, yes.
Okay. Okay. Um. Okay. So, do you guys want me to go over a specific question topic? To go over synthesis, predictive products, mechanism. Um.
Can you go over the synthesis, please?
Yeah, synthesis. Let's go over synthesis. Okay. So we have a terminal alkyne in the reactant going towards this molecule here with an alkene and alcohol and that R group right there. So what I like to do for synthesis is I like to highlight or keep track of my original molecule, which is going to be this 3-carbon chain right there, which is going to be that same 3-carbon chain right there. And I'm going to number it like this: 1, 2, 3. This is not the actual nomenclature way because the actual nomenclature would be like 1, 2, 3. But this is just for me to keep track of what my addups are. 1, 2, 3, like that. I see that this is the new group where I'm adding right here. And that new group has like a new carbon-carbon bond right here and an alcohol right there. So I'm gonna say that this terminal alkyne carbon here was my nucleophile, and this dot carbon was the electrophile, and this was the new carbon-carbon bond being formed right there. Right. So we could go backwards here. We see that there's a trans alkene in the product. Do you guys remember what kind of reagent or reaction can convert a term or internal alkyne into a trans alkene? There's 3 of those reduction reagents. There's H2PDC, there's H2 Lindlar's catalyst, and there's sodium in ammonia liquid, dissolving metal reduction. Which one of those 3 would make the trans alkene? Like, let's say we go backwards. Right, this is the star, this is the dot, new bond between them. Right. where we see that this is the 1, 2, 3. The triple bond or alkyne between 2 and 3, converting to an alkyne, would use sodium in ammonia liquid, dissolving metal reduction. That would make the transalkene. If you wanted the cisalkene, you would use H2 Lindlar's catalyst. If you wanted the alkane with no double bond all the way down to an alkane, you would use regular H2 PDC. But because we want the transalkene, we use sodium in the ammonia liquid. Now, we have to figure out how we could attach this new group onto this carbon right here, right? Because to make this carbon nucleophilic negatively charged, we could deprotonate it using NaNH2, and we could include the solvent, but we don't have to, which is going to give that carbon a negative charge like that, a star. And now I want my electrophile to involve some oxygen, right? And I see that it is going to be an epoxide opening. Right, and I'm going to draw the epoxide as wedge because we see a wedge bond like that on the other carbon. It takes up H3O+. This is in basic conditions. So we're going to open up the epoxide in the left subside, which is this red dot carbon right there. We're going to attack the epoxide and open up the epoxide right there. Where if I color code this carbon here in green, that's that green carbon right there. Right. But the way that I drew it here, it wouldn't actually be epoxide because the stereochemistry would not make sense. So I would have to like either draw it like this, which is the harder way, right? Or I would have to flip it upside down and draw it like this, which is the recommended way. Like that, right? Where this is the red dot, and this could be the green dot right here. The reason why it matters the way you draw it in the orientation is because of the stereochemistry, right? If we assign R and S to this chiral center here, this is 1, this is 2, this is 3. Going this way is S, and it stays S because the hydrogen in the back is a dash, the backside, so we keep it as an S. So that's why, like, you know, if you do this one, it's gonna be 1, this is 2, this is 3. Right here, it looks S, but it's not actually S. We flip it to R because the lowest priority group, hydrogen, is on the front. So because that's the case, we flip or invert whatever it looks like. It looks like S, so we invert it to an R. Whereas over here, wait. What did I just do here? Because I said both ways would work, so this would have to be S as well. 1, 2, 3. Okay, this right here is actually R. The way that I did it, like I rotated the wrong way. I said we rotated counterclockwise. That's the wrong direction because it's 1, 2, and then 3. That's clockwise. That's this direction, which is R. And we keep it as R because the lowest priority group is the backside dash. And this is also R because 1, 2, 3. 1, 2. Wait, no, that's not 1. What am I doing? Oh my gosh, what's going on? Okay, so this is the chiral center right here. This is 1. This is 2. This is 3. And going this way is counterclockwise. It looks S, but it's not actually S. We invert it to R, which is good, right? Because the lowest priority group is on the front side, so we just invert whatever it looks like right there. And we want to maintain the stereochemistry. So that's why this epoxide could work, or this epoxide could work, because that is also going to be R. And let's do it correctly this time. This is 1. This is 2. This is 3. Going this way, clockwise, is R. And we keep it as R. And that's good, because the lowest priority group, hydrogen, is on the backside already, so we don't have to invert it. right? So that's why the way that you draw the epoxide and the way that you orient them is important here on the reagent. So he might have taken points off from that. I don't know if that's going to be the key. But that's the synthesis right there. Right. This alkyl anion here can do 3 different reactions. One of them is epoxide ring opening, like this. The other one was SN2 with a primary halocane, and the other one was E2 with a secondary halocane. Okay. And then once we have this internal alkyne, we could convert it into a transalkene using dissolving metal reduction, like that. Okay. So this was a 3-step synthesis. The first step was an acid-base reaction to create the alkyl anion. Second step was epoxide ring opening in basic conditions. And then the last reaction was dissolving metal reduction to create the transalkene. Okay, any questions on this one? Now, I can give you a similar synthesis problems like this, if you want, or we can move on to a different question from the midterm to go over.
Ryan, I was wondering if you could also go over some Diels Alder.
Yes, Diels Alder. That is gonna be the complicated one. I won't have time today to go over everything on Diels Alder because there's a lot of things that goes with it.
No, it's just I was wondering if you could go over like when it goes like up or down, like for like the orientation.
Yes, the endo rule.
I had the same question.
Okay, yeah. You guys are good with the regional selectivity, right? Like the orientation of where the groups are supposed to be at, like when is it favorable, when is it not favorable? Because that's the first thing you look at before you look at the stereochemistry, like when it goes up and when it goes down, and the endo row. So assuming that you guys know all of that, I'm gonna give you my 3-step framework, step-by-step process on how I approach Diels Alder reactions, and then we could go through a lot of practice problems with that, and then hopefully it will click more. So the first thing I do for all Diels Alder reaction is I identify what my diene and dienophile is, because some problems, the way that they draw it is so confusing. Like it's hard to tell what the diene is and what the dienophile is. Once you identify that, what I like to do then is I like to orient them in this way, where the diene is facing this way and dienophile is facing this way, right? And that's the most important part right there. Diene right there, dienophile right here. Everything else is decoration, like whatever it is. It could be an EDG here, it could be another ring here, we could have an EWG here. Like everything else, ignore that. That's noise, that's distraction, that's decoration, right? The most important thing that's actually reacting here is this diene and this dienophile. Once we do that, then we move on to the second step, which is looking at the regio selectivity. And that's when you look at the charge alignment, right? We want the opposite charges to be in line with each other because opposite charges attract. And that's when you look at the EDG and EWG. And its resonance structures behind the scenes. Now, after everything is in line and you rotated, flipped, or translated it in a way that is in line with each other, then you look at the stereoselectivity of the reaction, which is the question that you asked about. And there's 2 things. There's the endo rule, and there's the dienophile cis and trans rule. We want to maintain the dienophile configuration. So the endo rule is gonna be like this. Let's say we have a diene like this and a dienophile like this. I'm gonna draw the pocket between the diene and dienophile right there, and that pocket is where the new bond is gonna be formed at. This is gonna be atom 1, this is atom 2, atom 3, atom 4, atom 5, atom 6. That's just how I number it. You can number it however way you want. but there's going to be a new bond between 1 and 6, 4 and 5, and then these bonds here are going to shift around like that in the mechanism. Now, when we talk about out and in groups, they're going to be referring to carbons 1 and 4. Out and in groups only on C1 and C4. So an out group is going to be a group outside of the pocket, facing outward of the system, outward of the diene. An in group is going to be a group facing inside the pocket, facing inward towards the system, like that. And this dienophile here is going to have some sort of EWG. Like, it could be anywhere. It could be here or here, anywhere. Like here, there, 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 there. And the Ender rule states that the out group is going to be cis to the EWG. The in group is going to be trans to the EWG. Okay. So that's the Ender rule. It's going to be more clear when we do practice problems, but the maintain dienophile configuration here is going to be like, if your dienophile has EWGs that are cis to each other, they have to stay cis to each other. And the harder example would be if they're trans to each other, they have to stay trans to each other in the product. And this one here could give you 4 different products here. This trans one here, and I'll show you why when we do practice. Okay, so this is what I think about when I do Diels auto reactions. Let's do a lot of practice to make it more sense. Okay, let's do this one here. And I'm gonna speedrun this. Stop me when I going too fast or when you have a question, and then I could explain my thought process on it. But I'm gonna walk you through it and explain it throughout. So, first thing, identify the diene and dienophile. Draw the pocket between diene, dienophile. Then I'm gonna look at the charges if they're aligned or not. This is an EDG, an R group. There's going to be a partial negative charge equally on both sides. These are EWGs here. There's going to be a partial positive equally on both sides. So they do align. That's good. We don't have to rotate anything. We don't have to flip anything. We could proceed with the mechanism. Okay, so when we draw out the base product of the Diels order, which is always going to be the cyclohexene right there, I can also number it like this: 1, 2, 3, 4, 5, 6, to keep track of where my atoms are. 1, 2, 3, 4, 5, 6. This right here is my in group. These right here are my EWGs. This is an in group because it's facing inward toward the pocket, and we said that based on the end of row, those in groups are trans to the EWG. So if I made that the wedge, then these EWGs would have to be dashes, trans to the in group. Right, this could be plus minus because, well, actually this one here, because this is meso, there's a plane of symmetry right here. There's no, this is achiral, right? Because of that plane of symmetry down that middle right there. But if this was asymmetrical, then we would put plus minus because it could have been flipped. Everything could have been inverted. So this right here is meso because of its symmetry, plane of symmetry. Another way that you could draw this to make it more visual is this right here. Right, where this is 1, 2, 3, 4, 5, 6, like that. And this wedge right there is this wedge right here. This is what we call a bicyclic ring. 2 cycles in the ring. Right, and that's because we have this CH2 right here. If I highlight that in blue, that's the CH2 right here. connecting carbons 1 and 4, which is still connecting 1 and 4, connecting 1 and 4 like that. Okay, so that's that first problem there. Let's look at the second one here and do the same process. Diene right here, dienophile right here. Let's look at the charge. This is an EDG right here. So this is an R group, so it can't donate electrons directly, but imagine if it was an OSH3 that can donate electrons directly through resonance like that, we would have a negative charge down there. This is an EWG, which is going to withdraw electrons by resonance, giving a positive charge down here. The charges do align. Opposite charges are on the same level, so we can proceed with the reaction. We don't have to flip anything. We don't have to rotate anything. Okay, so let's draw out the base template of the Diels Alder product, the cyclohexene like that. This right here is an out group because it's facing outside of the pocket. This is an EWG. And based on the endo rule, we said that the out group is cis to the EWG. Yep.
Question.
Yeah.
Do you align the partial charges together?
Oh, sorry.
Do you align the partial charges together?
Yes, we align the partial charges together. That's very important because sometimes your teacher or with some problems will give you questions like this. When you have, let's say, this EDG and you have this EWG right here. When you draw resonance, right, we can see there's a full negative charge there and a full positive charge here. And when you draw the pocket between the diene and dienophile, this is misaligned. This positive charge and negative charge are on opposite sides of each other. So because they're misaligned, this is not going to give you the right answer, right? Because some professors like to be tricky and students would just go for the answer right away. Like that, right? And give this final answer, but this is incorrect. Regioselectivity, because that's the first thing, the second thing you look for, right? That's the second step. Regioselectivity, align the charges together. We want the opposite charges to be in the same level. In this case, they're not. So this is the wrong answer here. To make the right answer, flip one of them upside down. I like flipping the dienophile upside down because it's smaller and easier to flip, just like that, right? And I'm just going to redraw the diene like this. And now we see that the partial charges do align now, which is going to give us our correct final product like that. So before you look at any stereoselectivity, endo rule, or dienophile configuration, look at the regioselectivity and the charge alignment, if they're aligned or not. Which this right here, with its enantiomer, plus minus, is the final answer. Like that. Okay.
Thank you.
Yeah. Okay, so this one does align, so we don't have to flip anything, we don't have to rotate anything. And because that's an outgroup and that's an EWG, based on the endo rule, the outgroup is cis to the EWG. We don't have to worry about the reason why yet. We do probably for explanation conceptual, but think of this as, let's say, predicted product. We're going to worry about predicted product for now, and then we're going to worry about the conceptual stuff later on. And why the endo rule says that. Okay. Now the next one here, this is the diene right here, and this is going to be our dienophile right here. This time it's a triple bond, not a double bond. So I'm going to redraw that like this right here, right here. Oh no, what the? Okay. Yep. 1, 2, 3, boom. Say ketone here, ketone here. This part of the molecule is the diene. This part of the molecule is the dienophile. Everything else is decoration and a distraction. The charges do align because these are EDGs, equally negative charge on both sides. EWGs, equally positive charge on both sides. Charges do align. We don't have to worry about flipping anything or rotating anything. Now, draw the pocket between the diene and dienophile. This right here is considered my in group. These are my EWGs. Based on the endo rule, the in group is trans to the EWG, But notice here, this alkyne here, when we do the reaction, does not convert into a single bond. We just take away one bond to make it into a double bond, which is why we don't get any wedges or dashes here. Everything is flat and planar. It is sp2 hybridized carbon. But there is still a CH2, CH2 connecting those carbon 1 and 4, like that. That's going to give our final answer. And another way that you could draw this is like this. Like that, right? And it's kind of like a basket with the handle, like that, connecting carbons 1 and 4. Okay, so that's that one. Let's do this one here. Okay, and then I will do the other three, which are, I would say, the harder ones, in tomorrow's office hours. But let's end off the session with this problem here. And this problem here, notice how the orientation of the diene and dienophile is oriented differently, right? So that's the first step. Identify where the diene is, which is that part, and where the dienophile is, which is that part. Then I just redraw it in a way where we are used to seeing it. Like this, right? And I'm going to specifically draw like this, just to show you why the way that we draw is very important here. Okay, where this is our diene, this is our dienophile. Be careful here. Don't close the ring right away and do the Diels Alder mechanism, because we gotta figure out the regioselectivity. This is the EDG right here on that carbon. So when we imagine it donating electrons towards the system, this can be a negative charge here. Imagine this donating a negative charge. This can be a negative charge on that carbon as well, through resonance. So our partial negative charge is right there. This is our EWG. So when we withdraw electrons from the dienophile, there's going to be a partial positive charge down here. So when we do the mechanism from this orientation, we're going to get the wrong answer. We're going to flip one of them upside down. I'm going to flip the dienophile upside down like that and maintain the diene the same, like that. Right? Now we could do the mechanism and get the right answer. This is our base cyclohexene right here. Let's draw the pocket between diene and dienophile. This right here is an out group. This is an EWG. The out group is trans to the EWG based on the Endo rule. Now you're going to notice that all groups on carbons 2 and 3 are flat and planar, and they stay flat and planar, right? Because carbons 2 and 3 will always stay sp2 hybridized in the reactant and the product. So there's no wedge or dash there. It stays flat and planar. And we could do plus minus here because there's no planar symmetry. Both of these could have been wedges, right? Because both of them has to be cis to each other. Out group and EWG, based on the Endo rule, cis to each other like that, right? So this one is a little bit trickier because they drew it in a weird orientation, and you have to orient them in a way that will give you to the right product with the right regioselectivity. And then once you get the right regioselectivity, then you can start thinking about the Endo rule, the out-in group, and the EWG. Now, these last two problems here are going to talk about the dienophile configuration, right? Like this is cis to each other, this is trans to each other, the two EWGs. And I would say that these ones here, especially this one, are one of the hardest reactions in Diels Alder that you see. And we'll do that in tomorrow's office hours, right? And we have this one as well to work through. But did that make sense on how to figure out what goes up, what goes down, and what is cis to each other, what is trans to each other, and the regioselectivity of where the groups are supposed to be at for this reaction? They're all going to follow this step-by-step process right here, right? Because in OChem, when you do like a lot of practice problems, I recommend you making your own steps, making your own process, and then when you approach a problem that does not match that, process that you make, that's when you change it, and then just keep repeating the problems out, and until you have a process that always works. I'm gonna change this process as soon as I find a problem that does not follow or agree with this process here. But this process is what I found so far that works for all Diels Alder reactions. The hardest one is probably this guy right here, right? Maintain dienophile configuration, right? Any questions on this? Those other stuff. This is really the hardest reaction for next midterm.
No, that was very clear. Thank you so much.
Yeah, thank you.
Yes. Of course, of course. I'll go over the rest tomorrow. Have a
Okay,
nice
thank
night,
you.
guys.
Yeah, you too.
Thank you.
Yeah.
Have a good night.
Yeah.